Okay, today the topic is basic of antennas, basics of antennas. So today we will be learning about some of the concepts of antennas that are to be known. When you are handling any kind of antenna, you should know the standards that are followed and other things, some uh, descriptions and some definitions, all these things you will see. So this is the fourth lecture, basics of antennas, and I'll give a introduction here. It's self-explanatory. I'll just read it. The radio telescopes are based on principle of optical telescopes. Radio telescopes uses antennas as the viewing instrument, and offline image is constructed later from the data using a pseudo color which can be seen with human eye. Thus, the prime instrument of radio telescope is the antenna. I think this is self-explanatory. In case of radio telescopes, you actually don't see the image directly. You have to construct the image, but you should also have a front end where a lens or something similar to lens has to be there, as in optical telescopes. That part is the antenna of the radio telescope. And then after collecting data over several hours, the data is reduced to form an image. And that image, since radio doesn't have any, how can you define that I see that object in radio having this color? So you have to give some color to that one. Otherwise, you will not be able to see. So whatever radio images that you see, they are actually the color or is not the same, but the shape is the same. The color is given to make you feel about the shape of the object. So in this chapter, we shall study the basic concepts of antenna theory from engineering point of view, which will be helpful in understanding the radio telescopes. In subsequent chapters, we shall enhance some of these definitions for radio astronomical usage. See, if you want to know how the radio telescope works, you have to know about the antenna, because it is the antenna is the primary instrument which actually collects data or signals from the radio source. So therefore, you should know that how the antenna follows the source, which part of the source it collects the waves from, which part of the source, all these things. So you should know what is an antenna is and how much power it is collecting, how is its relation with the outside world. So all these things has to be understood. And radio astronomy is, you can say, the technique of radio astronomy is engineering. The application or the people who are working in physics, who are astronomers, some of the astronomers who actually want to know about the object, they use this telescope and collect the data, and they reduce it using, again, softwares made by the engineers. So from the working point of view, everything is based on engineering. So here we are more focused on those things, that how you are making a radio telescope and how you are reducing the data. As such, astronomical things like you observe some astronomical object and that is the image, that is you form an image. That is the work of an astronomer. We will not talk about that. We will only talk about the internal things. So we start with the antenna, and from here most of the things will be engineering, as I said. The introduction has ended in the last session. So here we go. Now first we should know how an antenna radiates. I think these diagrams are okay, but this may not be very much explanatory, but I will just try to show it here. See, this is a transmission line. A transmission line consists of two conductors, and there is a equal spacing between the two conductors, and the space between them is filled by some dielectric. So this is a parallel wire transmission line, you can say, and the transmission line has some impedance. The impedance is equal to root of R plus j omega L divided by root of G plus j omega C, and all those formulas you will see. This comes in transmission lines, you remember that. And that impedance should be equal to the source impedance. Source is the signal which you want to propagate through this transmission line. So the source has also some impedance here, and this impedance should be the complex conjugate ideally, but then transmission line impedance is usually it consists of a resistive part only. There is no imaginary part. For practical, for practical purposes, we should choose a transmission line having no imaginary part in its impedance. So that should be equal to this one for maximum power to transfer from this source to this one. So if you are sending a signal to the transmission line, the signal will propagate along some direction, along this direction. Now you have gradually opened this transmission line out. Now you see you have increased this. Yeah. So what will happen? This electric fields were forming at any instant of time. This will be the electric field in this direction, and this is just a sine wave. You can see that this goes like this. This is the negative half cycle. This is a positive half cycle. Again negative half cycle, and then again positive half cycle. It goes like this, and this wave also travels omega t minus beta z. If you remember, e to the power minus j omega t minus beta z, where z is the direction of propagation, and all those things we have seen earlier in the first lecture. So this wave will be traveling out, and as you can see that since you have bifurcated this one, the energy density will reduce. That is, here the same energy is contained within these two lines, whereas that is getting here you are actually diluting it because you are opening it up. The same energy for that particular region will be distributed over this, so you can see it is fading out. Now here you can see the lines are straight, but here the lines gradually bend out. Okay, and so the waveform wavefronts, what it will be generated, will become spherical. Now these things open up after this. There is no transmission line, so these waves will propagate through the space and it will form loops. The distance between these two will be equal to lambda by 2. Now this is another view of this. You have opened the these transmission lines in a perpendicular fashion. Now you have opened it in inclined. Now if you make it straight, it will become a dipole. So this is a dipole. So in this dipole you can see that it is radiating in all directions except along this direction and this direction. It is minimum, but in these directions it will be radiating, where electric field is represented in blue, and distance between these two are again lambda by 2. And these red lines are the magnetic field lines. This is what it is actually. So and this will be going out. You must know that if there is no change of electric field, there is no wave. That means the electric field will be static. So in order to make a wave, you have to see that the electric field is dynamic or changing with time. So I will just read this one. This is the dipole radiation field. Electric field is shown here in blue and magnetic field is in red, and this I have taken it from Wikipedia. Now this diagram it says, due to the absence of transmission line conductors at this end, the fields join together and an electromagnetic wave is generated with spherical wavefront whose source is the signal generator connected at the input end. Okay, I think I have explained this. Now let us go to this one. There are some points which you should note. The power fed to an antenna from a signal source is radiated into free space as electromagnetic waves. Okay, it says that whatever power you have fed here, that actually is radiated in the form of electromagnetic waves. The reverse is also true, that is electromagnetic wave radiations falling on the antenna gets converted to power and is available at the antenna terminals which can be delivered to the load. The reverse is true means if some radiation is falling on this will get converted into a signal and it can be given to a load. Here you remove this one, you put a load here and you put some radiation on this one, you will see that the power has to go to the load. Of course, there are other things like matching and all that we have to see how it comes up. Then again, these two things make it clear that understanding the radiation properties of an antenna is equivalent to knowing its receiving properties. So that means the antenna receiving properties if you know the receiving properties, you can generate the transmitting properties of the antenna. And that comes under the antenna reciprocity principle. Here it is. The above properties of antennas are derived from the reciprocity principle of an antenna, which may be stated as the properties of an antenna are unchanged when used as radiator or receiver. Okay. Now we develop the concept of isotropic radiator, which I was talking about. We will see some diagrams in the next page. Let us see. Yeah, it is there actually. So the concept of isotropic radiator is that you have a source. Okay, for using an antenna, you always require a source when you are using it as a radiating element. So an isotropic antenna will have a source. You want to feed your power from the source to the isotropic radiator and you want to radiate it in all directions equally. If such an antenna exists, that is called the isotropic radiator. So I will just read it. The isotropic radiator or isotropic antenna is a fictitious radiator. It is defined as an antenna radiating equally in all directions. It is also known as isotropic source or simply unipole. So unipole is another name of isotropic radiator, and isotropic radiator doesn't exist in practice. It is just a measurement unit, you can say, or reference for measurement for other antennas, that how much it is it radiates more as compared to this one in a particular direction. So for all these purposes, this isotropic radiator is, this concept of isotropic radiator is used. So isotropic radiator is a concept. The isotropic antenna or radiator is a conceptual lossless radiating antenna with which any practical radiating antenna is compared. Thus an isotropic antenna is a theoretical reference antenna. Here there is one more thing. The isotropic, all antennas produces some losses. That is, you want your power to radiate out completely, but the antenna absorbs some of this power and it radiates the rest of it. The antenna is good if you are able to radiate maximum power of it from the source, only some power dissipates. It's best if you are able to radiate the full power. But then practical antennas do not radiate the full input power. In case of isotropic antenna, since it is a theoretical antenna, so you assume that whatever power you feed to this one, it has to radiate out. Now there are some exceptions. Though certain applications use a half-wave dipole antenna as reference antenna, but the use of the concept of isotropic radiator is preferred in majority of cases, since it gives a better understanding of distribution of radiation in three-dimensional space. Okay. In many cases, you take the reference antenna or the antenna based on which you measure your test antenna. For example, the gain of the test antenna can be compared with a dipole antenna. But then dipole antenna is a practical antenna. It cannot replace the isotopic antenna. It cannot replace that one. A dipole antenna is used for some practical purposes as a reference. So we will come to all of this as we go. Now, how to derive the properties of an isotopic antenna? So this is what it shows. See, this is a rectangular system, X, Y, Z, and we want to put our source here. This source is nothing but an isotopic antenna connected with a source. We want to see what are the properties of isotopic antenna quantitatively. We want to see that one. So this, in this X, Y, Z coordinates, you construct a spherical coordinate system. So in spherical coordinate system, you have theta and phi and r. R is this in this direction in the sphere. This radius r. R is the radius of the sphere, and the where it is in the sphere is specified by these two angles, this theta and phi. So we want to know how much power is radiated from this one, which passes through the entire spherical surface. I mean to say that you consider a sphere of radius r, and we want to know how much power passes through this surface. If we are giving some power to this one, we assume that all the power is radiated. We want to see how much power is there per unit area on this surface. So first we calculate a small elemental surface. So this elemental surface you can calculate by, you have to have this length and this width, and if you multiply it, you get the elemental surface area, and when you integrate it over these limits for theta and phi, then you will get the entire area of the sphere. So this is it looks complicated, but if you do it, it will be very much simple. Now this length is r sin theta d phi. If you see, this is r sin theta means you take a projection on this one. This is r sin theta, and d phi. So this is phi. So d phi has to be this one. This elemental area is d phi. So this one is r sin theta d phi. So it is justified. What about this? This is in d theta. So this is theta. So this has to be d theta. So this radius multiplied by d theta will give you this length. When you multiply these two, you get this area, that is ds, that is r square sin theta d phi. Now power Wt radiated from the center passes through the sphere surface area 4 pi r square. If you integrate this one, you will get the area of the sphere, provided you put the limits of theta and phi. So in this case, you can see that theta varies from 0 and from this point to the below if you increase this z to minus z. So from this to this, so theta limits varies from 0 to 180 degrees, whereas phi is in this plane, it will be 0 to 360 degrees. So when you integrate this one, double integral 0 to 180 degrees, 0 to 360 degrees respectively for d theta and d phi, then what you get is 4 pi r square. So that is the area. Now the power density, that is the power per unit area at a radius r on the sphere of the radius r on the surface of the sphere is PR. So we define PR as the power density, which is the power per unit area at a distance r or at a radius r on the sphere. So this, what you will have to, how do you calculate this one? you will assume that this is having a power Wt at this point, which is radiating in all directions. So you want to know what is the power per unit area on at a distance r or radius r. So what you will have to do, you will have to calculate the area of the sphere at a distance r, or at a sphere of radius r. You have to calculate the surface area of the sphere. So you calculate it this way, and then you divide this power with the surface area. So you will get that power per unit area. So this is what it is. Pt is equal to Wt divided by ds, where ds is this one, and we saw that ds is equal to 4 pi r square. Here is the integration which I was talking about. So phi is integrated from 0 to 2 pi, and theta is integrated from 0 to pi. And this one, if you integrate it, you will get Wt divided by 4 pi r square. Now, the right hand side of the above equation is known as the inverse square law of radiation. So this 1 by 4 pi r square, 1 by 4 pi r square is called the inverse square law of radiation. This is the source. So if you assume that a source transmits in all directions, so you can see that the power will be 1 by r square. It will be proportional to 1 by r square per unit area. So that is why it is called the inverse square law of radiation. This square law means r to the power 2. So this is the meaning of this. So isotopic radiator and inverse square law. So I will go to the next slide. Now here this diagram actually shows that, okay, this doesn't tell you exactly I mean to say that these regions are not very well defined. That is, you cannot consider this region to be certainly at this point, but these are only approximate. So a radiating structure can have 3 regions. I mean, we have classified in 3 regions. One is the reactive near field region, another is the radiating near field region. This is called the Fresnel zone or Fresnel zone. I don't know how they spell it, but I think it is Fresnel zone. That is the correct way of spelling. And anything beyond that is called the far field region, known as Fraunhofer region. So you might have noticed that when you take measurements of an antenna, you would like to have it in the radiating zone or radiating far field region, or this one, because you maintain certain distance from the antenna. The reason is the energy that will propagate has got 3 terms. One varies with 1 by r, another by 1 by r square, and one proportional to 1 by r cube. So the 1 by r term comes here, and 1 by r square comes here, and 1 by r cube comes here. This is I am talking about the field. The field, for example, if you take the electric field, in this place, the electric field as a function of distance r, this radius r, will have 3 components: something proportional to 1 by r, plus something proportional to 1 by r square, plus something proportional to 1 by r cube. So as you increase, the term with 1 by r cube will diminish very fast. The term by 1 by r square will diminish slowly, and term of 1 by r cube, 1 by r will diminish the least. So this region in which the 1 by r cube term comes to an end, this is called the reactive region. This is about the field, electric field, not the power. Then here you will see that this will be 1 by r square term will come to an end here, but 1 by r being decaying slowly, it will remain, and this is the one which actually offers is responsible for radiation of an antenna. 1 by r term of electric field and 1 by r term of magnetic field. And when you take the power E cross H, that is the Poynting vector, then it will be 1 by r square. So the here you see that the power propagates as 1 by r square. Here it is. So here in E cross H, if you see that it is proportional to 1 by r square, that is that power. Maybe if we have something, we can see more equations on that one. But for the time being, you can remember it easily. You have three regions: near field, radiating near field, and reactive near field, radiating near field, far field region. Now, this value of R is defined as 0.62 root of d cube by lambda, where lambda is the wavelength. So every antenna that you fix here will have will be operated at a particular frequency to which this lambda is calculated with that reference. And d cube, d is the maximum size, or the antenna consists of many elements. So you will take the largest size of that element, that is d, and you calculate this R1 and R2. So R2 is again 2d square by lambda. So I will just read it in case I have missed something. The field patterns generated by a radiating antenna vary with distance and is associated with radiating energy and radiating energy and reactive energy. The space surrounding an antenna can be divided into three regions: reactive field region, this one, then radiating near field region, this region, and radiating far field region, this one. The boundaries of these regions are not defined precisely but are only approximations. Reactive field near field, this R should be less than R1. So this one here, you will get all the components of the electric field, and then in this radiating near field, between this region and this region, that is R1 less than R and less than equal to R2, and D is the length of the largest element in the antenna. This is okay, na? Okay. Now we come to radiation patterns. If you, I mean to say that if you miss something, if you think that you are not understanding, just ask. I will try to answer that. Now we come to radiation patterns. Yeah. So this is a dipole here. The picture is not. I think you can see that there are two elements of the dipole. This is a half wavelength dipole. And this element on the top is the quarter wavelength long, and this is quarter wavelength. So both of these together, they form, say, the total length will become half. And a source is connected somewhere here, and this is in 3 dimensions. If you can remember the radiation pattern of a dipole as an apple. So this looks like an apple, you can see. This is in 3 dimensions. So what does this mean? It means that the radiation will be more in this direction. You can see here this surface exists, but here you see it has gone down. So that means the antenna will radiate least along this direction and minimum at the center is along Z. Along Z it will radiate minimum because the apple is dipped. Similarly on this side also you can see that the apple will dip on this side, so it doesn't radiate on this in this direction, but it will radiate in all directions towards us and away from us, perpendicular to this page and all. Now a 3-dimensional radiation pattern is difficult to handle. Handle means well, for seeing and understanding is good, but then when you are doing it on paper, you need to use simpler diagrams like these two. So if you get the information of the radiation pattern on 2 planes, orthogonal planes, or 3 orthogonal planes, I should say. Orthogonal planes means Y, Z plane. This is one plane. If you cut the radiation pattern, you want to see how this forms lines on that one. Then you cut the radiation pattern in Y, XZ plane, and that is another information. And then you cut it in YX plane, XY plane. You get another information. So these 3 informations are sufficient to show the radiating properties of an antenna. In case of dipole, you know that cutting it in YZ plane produces the same pattern as cutting it in XZ plane, so you need only one. So these are the things what you get. When you cut it in one of these planes, say YZ plane, you will get two circles. So you see that radiation is more and more, and it increases. In this direction it is maximum, whereas in this direction it is minimum. Whereas if you see in this plane, XY plane, here it is, you see that it is radiating equally in all directions. This is a slice of 3D pattern and slice of 3D pattern in XY plane. So I'll just read it in case I missed something. Radiated power from practical antenna is more in some particular direction and less or null in some other directions. So less or null in some other directions. So this is one of these you can say. The energy radiated in a particular direction is measured in terms of field strength or flux density at a point which is the fixed radial distance from the center of the antenna. The measurement must be done in the Fraunhofer region. So if you want to measure the, as I said earlier, that if you want to measure the radiation properties or radiating properties of an antenna, you have to do it in the Fraunhofer region, where the other fields, other components of the field doesn't exist. Only the radiative field exists. Okay. Now, here in this diagram, this is a general radiation pattern. Of course, these are side lobes. This is the main lobe. Of course, the side lobes doesn't look exactly like this. They will be. This diagram shows that this is like a ring, but it is not like a ring. It will have again bifurcations in between. There can be several such lobes out. Something like this one coming out in different areas. This is called the back lobe, and you have to bear with this diagram because it's not drawn to the expectation. I have to correct this diagram. So this is a three-dimensional view of the radiation pattern. This only means that if an antenna is placed, if the antenna is placed at this point, X, Y, Z, at the center of this point, then this will radiate more in this direction, maximum. It will radiate slightly less here, 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 and after this it will not radiate until it comes here. It will radiate slightly in this direction, and again it will not radiate, and again it will radiate something, and again on the back side it will radiate. This is what it means. Now, from this three-dimensional pattern, you can cut it, and let us say here it is YZ plane. In that YZ plane, you cut it, and you get this one, a two-dimensional view of the same radiation pattern. Now, you have to have something with which you can say that okay, the antenna radiates so much power in so much direction. So for that you need to have some tool. So for this you have people have defined some of this, like half power beamwidth and beamwidth between first null. These are some of the terms which they have defined. Everybody is interested. The designer of the antenna is interested to make the power propagate in only one particular direction, and you don't want the side lobes or the back lobe. But then whenever you design an antenna, however good it may be, you will always have some back lobe and side lobes. Back lobe and side lobes you will always have. So in order to measure this, different concepts has been created. Then how much power, how much is the beam efficiency, and all these things. So we are going into these things actually. So this portion is called the main lobe, and these are the side lobes. And here the radiated power is maximum. So the half of this will be somewhere here. Half of this total length will be somewhere here. If you cut this one with that with a line here, or a round kind of this kind of line, curved line like this, then you will see that this line cuts this beam into 2 points, and these 2 points are exactly the half of this length, here and here. And if you construct an angle between that, or if you measure the angle between that, that is called the half power beam width angle. Whereas after this major lobe, there will be side lobe. So between major lobe and side lobe, this point is called the null point. So if you want to take the full beam width of this one, so you have another definition, that is beam width between first nulls. So this is the first null on this side, second null and first null on that side. This should be called second null, third null from the main lobe. So beam width between first nulls is these are the lines on which this angle is defined as the beam width between first nulls. Now instead of this polar kind of picture where you are rotating the angle you are rotating it like this, you plot this versus angle and you take it in a rectangular coordinate. You plot the angle in a rectangular coordinate. Here you are plotting the angle in a circular way. Here you are putting it straight up. So you will see that this pattern will break up like this. So this becomes more easier to understand. So here is the 0 degree. Usually we take 0 degree in the main beam center, main lobe center. Now here you can see the side lobes and back lobes, and these are the null points. This one, this one, this one. These are the null points, and you can see that if this is the maximum radiation, then half of it is this one, and this angle, if you take this angle, that is the half power beam width. This one. This is the back lobe. So I'll just read it in case I have missed something. Generally, antennas are oriented in such a way that at least one of its principal plane patterns coincide with the geometrical plane. Lobes of a radiating pattern with main lobe oriented along an axis. So I will move to the next slide. Okay. So again, we are going through the same definitions. We are seeing some of the other aspects of this. So lobes and beam widths, and I'll start reading from here. Between two adjacent radiating regions, there exists a very low radiating region called null, which I described earlier, this and this. Of course, the radiation from this is not exactly zero. It is minimum, or as compared to either sides of that one. But it may not be zero. So this is what it says. Low radiating region called null. Region between two nulls is called a lobe. So you describe the lobe as, this is one lobe. This is between two nulls. The region between the two nulls is described as a lobe. The lobe associated with peak radiation is called main lobe. So this is the description of the definition of the main lobe. The lobe which is associated with peak radiation. This is the lobe which gives peak radiation, and so it is called the main lobe. Here it is written. The others are called side lobes. The others means rest of them, except the last one which is just directly opposite to this one. That is the back lobe. This one. This has to be opposite to the main lobe. The lobe which is opposite to the main lobe is called the back lobe. The angle at which the peak radiating power or the main lobe falls by half or either sides is called the half power beam width, or HPBW. This I have already spoken about. And then the angle subtended by the major lobe between two adjacent nulls is called the beam width between first nulls. That also I have explained. This is beam width between first nulls is between these two. Then there is one more definition. This is called the front to back ratio. And the front to back ratio is defined as the power that is radiated along this direction, and the power or from this diagram you can see the power that is radiated along this direction to the power that is radiated along this direction. So this is the front side, this is the back side. So its definition is FBR, front to back ratio, is equal to radiated flux density from the center of the major lobe. This is the center of the major lobe divided by radiated flux density from the center of the back lobe. So in this direction. So this ratio is called the front to back ratio. So the front to back ratio actually tells you how good the antenna is in radiating in the required direction. This is your required direction. So if it is very large, so you know that most of the power is radiated in this direction, whereas minimum is radiated in this direction. So the antenna is good. But of course, it doesn't. It is not. It is just a partial way of defining a good antenna. There are other parameters of the antenna that has to be verified before it should be said that it is a good antenna. So this is one of them. Now we calculate. We know that the radiation patterns, they are not same in all directions, because you can see this particular kind of shape and all. And instead of taking the absolute values, can we just normalize this one? So we consider that this point, if we normalize it to unity and consider other points to be less than unity and plot the pattern. So that type of pattern is called the normalized radiation pattern. If it is for the power, then it will be a power pattern. Now you see here on this sphere I have drawn here along this x, y and z coordinates. Theta is equal to 0 as it goes like this, and theta is equal to 90 degrees in the opposite side, and this is the movement of your phi. All are marked here. Phi is equal to 0 degree, theta is equal to 90 degrees, phi is equal to 90 degrees, theta is equal to 90 degrees. So these coordinates has been marked here. And this diagram is self-explanatory. This is a black back lobe, and these are the nulls, and then side lobes. And what is important here is, see, the wave coming from this antenna will be propagating along this direction, this direction, this direction, depending on, and the amplitude will be dependent on this shape. So on the surface of the sphere, if you draw two orthogonal lines or vectors, one will be the direction of E phi and another will be the direction of E theta, or the electric field along this direction is E phi and along this direction is E theta, and the pointing vector will be perpendicular to this. That is in this direction. You can see that E vector, E with arrow on the top. These also are vectors. So if field is a vector, I have not drawn arrows over this. So consider these two as vectors. We place an antenna at the center here. The electric field components are E theta phi, because E theta function of theta and phi. This means that E theta is the function of theta and phi, and the other electric field component will be E phi, that's also a function of theta and phi. The radiated power will be in the direction of the pointing vector, this one, and this is equal to E cross H. The pointing pattern E cross H, we have already seen this one in the first lecture, this from Maxwell's equation, so we have come to that. And the power pattern is S theta phi. Power pattern means this one, this radiation pattern is constructed by measuring the power on the surface of a sphere of constant radius at different points, and then this pattern was created from there, and that is a function of theta and phi as well, this pattern. So this is the power pattern S theta phi. The normalized power pattern is En theta phi. So when you divide S theta phi by maximum of this value, what you get is Pn theta phi. So you have to have for a normalized pattern, this point should be unity. That is what it means. Now, yeah, the expressions are given here. Normalized electric field E theta phi with a subscript n is equal to E theta phi divided by maximum value of E theta phi, and again the power pattern is equal to this expression comes from Poynting vector, and you have to convert the magnetic field energy in terms of electric field by its relationship with Z0, where Z0 is the impedance with free space. That is why this expression has come. So as if you remember, an electromagnetic wave will have for a plane polarized electromagnetic wave, the electric field will be in one direction and the magnetic field will be perpendicular to it. Now this magnetic field has a relation with the electric field. The total energy of the electric of the wave is the sum of the electric and magnetic fields. Now the magnetic field also you can express in terms of electric field by using the intrinsic impedance of the free space. So the total energy will be the electric plus magnetic field. So here it is. So this expression comes because of this. Now Z0 is the characteristic impedance of free space. Normalized power pattern Pn is equal to pattern divided by its maximum value. The power pattern divided by its maximum value. These are very easy things I am reading out. I don't know, people may get confused. I am not able to explain it nicely or so. But these are very easy things, particularly normalized electric field, these descriptions and all, although the expressions look somewhat otherwise. Okay. Now we come to the concept of antenna beam solid angle. These are again since the radiation pattern is something which is very difficult to categorize it into different things. So that is why several kind of definitions and other things are used for our intuitive understanding of the radiation pattern. Sometimes it is easy to compare beam width using common standard, namely beam solid angle. Again, this is for understanding the properties of the beam width. Now this is a practical radiation pattern. Or here the diagram again, the side lobes are not drawn properly, and you have some geometrical shape type of beam width. This again has to be fictitious because practical beam widths will be like this. And here it is a fictitious beam pattern for calculating the beam solid angle. So the solid angle is the angle subtended by this cone. Theta HP and phi HP are the half power beam widths. This is omega A. This is the okay. I will come to all of this. Now you take a two-dimensional comparison of this and this, so things becomes more clear. So we define beam solid angle as a conical form of angle like this, but actual antenna will have something like this kind of pattern. So we want to find what will be the equivalent of this practical pattern in this shape. Can we form an equivalent beam solid angle from this pattern? That is what we want. So the definitions comes here. If power radiated from both these patterns are same, the solid angle omega A is defined as the beam solid angle. That means if the power radiated by this pattern and the power radiated by this beam solid angle pattern are same, then this pattern is the equivalent beam solid angle of this pattern. That is what it means. And it is defined as again you have to integrate it over the sphere, normalized pattern or integrated over the entire sphere, and that is equal to, almost equal to the half power beamwidth in two planes. One is XY, you can see it in the previous diagrams. So these are called half power beamwidths in both planes. And d omega here, this one is the elemental area on the surface, the sin theta, d theta, d phi. Now, two things to be noted are side lobes are included for calculations, and fictitious pattern radiates at peak intensity of the main lobe. And of course, this I forgot to explain. If you see this diagram, you have to, how do you form this this one? First, you draw a circle or a part of a circle, semicircle here, which touches this one. So that means the beam solid angle's radiation should be same as, will be same in all directions within that angle, and also it has to be equal to the peak intensity of the actual pattern for which you are making. So if you can, that thereby you can increase this angle on this side or and this side symmetrically and form an equivalent pattern which should radiate the same amount of energy per unit time as that of this one. So this is how it is. First, you have to see that this maximum of that should coincide with the maximum of this. Now again so more about the beam solid angle. We know that the beam solid angle is given as this angle, this solid angle omega A is equal to this expression, and which is approximately equal to this half power beamwidth product. So some power is radiated by the side lobes. Thus the solid angle omega m of the main lobe is much less than the beam solid angle omega A. Ideally, we don't want this to happen in case of any radiating antenna, in case of any practical or in any antenna. We don't want these side lobes. But then side lobes do occur, and because of their presence, they will divert some of the energy in these directions also, though it may be negligibly small as compared to this one. So this is the reason, I will read it again. The solid angle omega m of the main lobe is less than the beam solid angle omega A, and it varies from less than 100% to 75% of omega A. Thus we introduce a factor Kb in the following equation. So if you don't have these side lobes, then Kb has to be unity. So you can express this one as a function of Kb into theta half power in both planes, and that is what it is. And this value of Kb lies from 0.8 to 1. So there are some problems at the end. You can use this and you can solve them. Now we come to the antenna beam efficiency. Somebody has to tell about T. I have forgotten about that. I didn't say, and Mrs. Deshmukh was supposed to come, but she has not come. So in that case, I will just take a, no, I will continue. Somebody please inform the canteen. Yeah, please inform. From there you can inform 30310. There is the number of the canteen. You tell the number of people are there and send T immediately for lecture. You can tell that. So there are other definitions like antenna beam efficiency and stray factor. These actually again help us to understand the properties of the antenna. Now these are very simple relations. You can read this one. The distribution of radiation over the sphere is not uniform for any antenna. Again, the same thing. At certain points, there seems to be no radiation at all. There is a null point. The shape of the antenna beam can give a rough estimation of what fraction of power is radiated in the required direction. So the beam efficiency is described here. Ratio of solid angle of the main beam to the sum of solid angles subtended by all lobes. All lobes means including the main lobe. So each one has a solid angle. Each one of this lobe has a solid angle. So you sum them. That is the sum of solid angles subtended by all lobes and the solid angle subtended by the main beam. So you have to find the solid angle subtended by this main beam. You have to find the angle in both planes, and you have to find out what is the solid angle. Now this is the this beam efficiency. You can say that this M stands for main beam, epsilon stands for efficiency. So this is what it is. Solid angle subtended by the main beam, that is omega M, divided by solid sum of solid angles subtended by all lobes. And this is also related to this. This is called the stray factor. The ratio of sum of solid angles subtended only by minor lobes to solid angle subtended by all lobes. That means here you have for the major main lobe, you remove it and you put only the side lobes here, and this divided by the total solid angle consisting of all lobes. So this is what it is. Epsilon M, small m here, it is small m, sum of solid angles subtended by the minor lobes by sum of solid angles subtended by all the lobes. Thus the sum of these two factors is unity. If we just sum these two, it comes to unity. Now again, I'll just go for some little bit of recap. This is what we have studied earlier in the first lecture. So electromagnetic waves travel through free space. A large distance from the source of radiation, the power available per unit area, that is the average power over a unit area, can be obtained from the average value of the Poynting vector given below. P is equal to average of this Poynting vector, that is E cross H, and that is equal to half of real of E cross H. So these two are complex. When you take the evaluate this, it will have a real and imaginary part. You are taking the real part of it, multiplying it by half. This much amount of energy or power per unit area, that is expressed in watts per meter square. Here P is the instantaneous Poynting vector. E and H are the instantaneous electric and magnetic fields. E and H star are H star means it is a complex conjugate. E and H star are respectively the scalar values of time varying electric field and complex conjugate of magnetic field. Yeah, I think yeah, H star. This should be H star actually. I have not marked here. If E and H are respectively expressed in volts per meter and amperes per meter, then the average value of the Poynting vector is in watts per meter square. So these two, if you multiply these two volts per meter into amperes per meter, so volt into ampere becomes watt, and meter into meter becomes meter square, so watts per meter square. Now we come to the radiation intensity. This is another definition, and these definitions are simple. Though you may be getting bored, because there is this is what happens in engineering, and also this is radiation intensity U, defined as U. It is the power emitted over a solid angle from an antenna. It is independent of the distance and is expressed in watts per steradian. Now, in earlier cases, we were using watts per meter square. here we define a quantity called radiation intensity, which is defined as watts per steradian. So you see, this is independent of the distance. This unit is independent of the distance. It is dependent only on the solid angle, and it is called radiation intensity, defined as U. So again, I have already explained this diagram, so I don't want to explain it here again. So ds, this area is equal to r square sine theta, d theta, d phi, and solid angle subtended is equal to this, and so on. So total solid angle of the sphere is given as, you have to integrate it over this, and you get it as 4 pi. So what is the total solid angle of a sphere? In earlier case, we were calculating the total surface area. Here, the difference between the earlier one and this one is that we are calculating the total solid angle of a sphere. So if you substitute in this here ds and all these things, and if you integrate it, what you get is this 4 pi steradian. That is the total solid angle of a sphere. So in case of a isotopic radiator, the radiation intensity will be W divided by 4 pi. And here, Uy is equal to W divided by WR divided by 4 pi. And radiation intensity U is equal to infinitesimal power divided by infinitesimal solid angle. That is the definition. We have done it here. And this is D stands for infinitesimal, dW and A. And normalized power pattern has a relation with this one, that you have the radiation intensity in any direction divided by the maximum radiation intensity, so it becomes normalized, and that is equal to the normalized power pattern. So this diagram is same as other diagram. I have only just brought it here to give a feel for this again, and spherical coordinates. And one more thing I just wanted to, I forgot to mention. See, some physicists use a different, the spherical coordinates, in spherical coordinates there is some confusion. In some books you will find that this theta and phi are interchanged. So engineers prefer theta and phi to be like this, whereas physicists prefer theta to be here and phi to be there. So there can be some confusion. So whenever you are using spherical coordinates, you should be careful about that, where they have placed theta and where they have placed phi. So it's very important, because after all, if you are doing serious calculations, then you find at the end your results are wrong. So be careful about it. And I think mathematicians also prefer this phi in this direction and theta in that direction. Well, that's out of concern. Then, antenna impedance and radiation resistance. These are some of the things we will define here. The antenna shows an impedance at its input terminals consisting of a resistive and reactive part. This real part is responsible for radiation and power loss. Okay, if you have an antenna and if you put that antenna in free space, if you measure if you have a source at its input, you measure what is the source voltage and what is the source current. So if you divide the voltage by that current, you will find a value, that is the impedance, and that impedance is the antenna impedance, and that impedance you will see that it consists of a real and imaginary part. So this is the antenna impedance. The antenna dissipates, okay, again this real part is responsible for, okay, I will read it here. The antenna dissipates the power fed to it. If the radiated power and the dissipated power are respectively represented as WR and WL, then the total power WT consumed by the antenna is this one. So this is the total power. This consists of a part, this is the radiated part, and this part is the loss of the antenna. The antenna doesn't radiate this much power. So it takes this much power, it radiates this much power, and it consumes this much power. If I is the current flowing through the antenna at its terminals, we may express the total power WT consumed by the antenna given as. So only thing is that you are just breaking up this equation, that I square R, that formula you are using, and you are breaking up this equation, and where I is the terminal, is the current at the terminal of the antenna, and so you can express it as RR and RL, and this RR is the fictitious resistor known as the radiation resistance of the antenna, whereas RL is called the loss resistance. So in general, you can say that antenna consists of produces some loss. If you give some input, it will not radiate the full input power. Some power will be radiated and some power will be consumed by the antenna. It will be generated as a heat and within the antenna, and it will be consumed. And the power that is radiated, there is the equivalent resistance which can radiate that much power is called the radiation resistance, and the equivalent resistance which consumes the lossy power, the power which goes into as losses, that is this RL. So you can remember like this. So I will read again. Here RR is a fictitious resistance that would consume the amount of power lost in radiation. It is known as the radiation resistance. RL is the resistance that would consume the amount of power lost as heat. It is called the loss resistance. For an ideal antenna, this RL should be equal to 0. It has not come properly here. So, if the antenna is ideal, then it should not have any loss. So this part should be 0. Now I will say one thing. Radiation resistance doesn't really exist in an antenna. Physically, it doesn't exist in an antenna. It is a fictitious resistance. You should know this one. It doesn't physically exist in an antenna. It is an equivalent resistance which describes how much power it is able to radiate out. So it's just a measurement. Though you may hear engineers talking about what is the radiation resistance and all these things, but remember that there is no resistance in an antenna. Physically, there is no such resistance. Now we come to antenna efficiency. I will first read it out. The power efficiency of an antenna, you will understand this because you have already gone through the previous slide. So this is easy to understand. The power efficiency of an antenna, or known as antenna efficiency, is the ratio of power radiated to total power input to the antenna and is denoted by eta subscript A. So this is the definition, and this is the definition of antenna efficiency. A and the subscript A stands for antenna, and generally this symbol eta is used for efficiency. So antenna efficiency is equal to power that is radiated by the antenna divided by power that has been given to the antenna. Thus, if the radiation resistance RR and the loss resistance RL is known, the antenna efficiency can be expressed as, if you know these two values, you can simply express the input power as radiated power as I square RR and input power as I square into RR square plus RL, and so this simplifies to this. Where I, you have already I have described this. I is the current flowing through the antenna terminals, and again you can convert it into percentage efficiency by multiplying this eta underscore A with 100. So it will be in the percentage. This is very simple but very useful concept. People should remember this. This is very useful concept, antenna efficiency. So when you are designing an antenna, you should design it in such a way that your antenna efficiency is much higher. Generally, the antenna efficiencies will be something around 0.9 to 0.7 for a fairly good antenna. But below that, the antenna efficiency below, I mean, efficiencies below 0.7 and all, they are not considered as good antennas. They will consume a lot of power as losses. And the antenna efficiency depends on how you match the antenna. That means the antenna terminals, you have some impedance, and then you have to match the source impedance with the complex conjugate of that to have a maximum power transfer. And if the matching is not good, again the matching also is frequency dependent. If you have a wider bandwidth antenna, it is very difficult to match. But if you have a very narrow bandwidth antenna, so these are some practical considerations. So in principle, you cannot make an antenna 100% efficient. There has to be some losses. There is one more concept called the antenna directivity, and related with that there is another concept called antenna gain. So directivity and directive gain and normal usual gain, these are the things we come here. I think we are almost done. So all practical antennas concentrate more power in one specific direction. We know that. It is of interest to see how much power is concentrated in a particular direction by the antenna. The antenna directivity may be visualized as the extent which a lossless practical antenna concentrates the radiated power related to an isotopic radiator. So what we want to see is that we always aim for making antenna which concentrates its radiation in a one specified direction. We don't want the antenna to radiate in all directions. So how good that antenna is? So you will have to compare that how much it radiates power in that given direction as compared to the to that of an isotopic antenna which radiates in all directions. So that comparison, if you do, that comparison is the defines the directivity. So we will see how the directivity is related. The directivity D is the ratio of maximum radiated power density to its average value, or another definition is maximum radiation intensity to radiation intensity of an isotopic radiator. You see, it is just a comparing itself with the isotopic radiator. So that is why I said that isotopic radiator is very important, though it is a theoretical concept. So its dimensions, it is a dimensionless quantity. So this directivity D is usually represented as D. This is actually dimensionless. So here you see, this is the maximum value of P. That should be unity actually, and this is the average value of P. The P is the you can say it as okay. This can be normalized pattern in which I am giving one more here. Then this would be unity, and this is the average. Then this should be the isotopic equivalent, or the maximum power radiated. The maximum power radiated divided by the average power radiated, or this is equivalent to the maximum radiation intensity, this one, and divided by the average radiation intensity, or UI is the radiation intensity of an isotopic radiator, and this comes out to be 4 pi by omega m, where omega m is the solid angle subtended by the main beam. These definitions are here, descriptions are here. P theta phi max is the maximum and respectively mean average isotopic. Okay, all these things I have said. Okay. Now we go to the, how many slides are there? Okay, I think we have more. Okay, so this is another expression how the directivity is related with the half power beamwidth. So this is in the theta plane and this is in the phi plane, and this is simply as 40,000 divided by these two. This expression you can find in the book written by Balanis. also in the book written by Krauss. This is a very simple expression. You can remember it. Or just you remember that D is reciprocal of these two. You multiplied by some constant. That will be easier to remember. Then there is one more quantity called directive gain. Now, directivity was focused in one particular direction, whereas the directive gain, usually termed as G underscore D, is the quantity directivity for all theta and phi, or in that way, or you can say that a similar kind of quantity, but in all directions, whichever direction you want, you have a directive gain, and that's a function of theta and phi. Unlike directivity, which is specific to the direction of maximum radiation, the directive gain GD is used for any direction and is expressed here. Again, this P, theta, phi, and this are same as before. This is the radiation intensity, and this of isotopic antenna, the radiation intensity of isotopic antenna, UI. So I will go to next slide. So another concept similar to directive gain is the gain or power gain. So you can consider that this is directive gain GD, and this is power gain. If you forget this one, you have to put a proportionality sign. So you will see that power gain is similar to directive gain, but power gain is concerned with practical antennas which is having loss, whereas directive gain considers the antenna to be lossless. So the relationship ends with the antenna efficiency A coming in between. So I will read it. Another concept similar to directive gain is the gain or power gain, usually denoted as G or GP. It can be sometimes represented as G. The directive gain GD and the power gain GP of an antenna are related by antenna efficiency and expressed as this. And there is the antenna efficiency, which is less than unity for all practical antennas. Also note that power gain is always less than the directive gain. Okay. This factor is always less than unity. So the power gain will always be less than the directive gain. These are very simple expressions, you can remember it. Now there is a concept called effective aperture area of an antenna. The concept of effective aperture area has been developed based on receiving antenna. Let us assume we have a device which converts electromagnetic energy into electrical power at its terminal. The amount of electromagnetic energy collected is proportional to the collecting area. This arises from the fact that electromagnetic energy is measured as a flow of energy per unit time per unit area across the frequency bandwidth. In other words, it is flux density. Okay. See, you know that the electromagnetic waves are spread out in space. If you want to collect energy from the electromagnetic waves, then you have to collect the electromagnetic waves over certain area. The more your area is, the more amount of power you can derive from the electromagnetic waves. That area, so in the antennas also collect some portion of the electromagnetic waves spread over some portional area. Okay, and each antenna has a different capacity of sucking the electromagnetic waves. So then, all these are related with area and the electromagnetic flux density. So the more the area or more the flux density, then you get more power. Considering flux density as constant, you have to work on the area. So antenna should have some area which is called the aperture area. So if we say the antenna has more aperture area, it will get more power. It will convert more electromagnetic energy into power. So that is some way of understanding what is an aperture area. So now we have to define that one. That's only a physical description. Now we have to define it. The amount of power P antenna received by an antenna is the product of fictitious area called the effective aperture area, AE. So this is the definition. The power of an antenna received, the power that an antenna produces after receiving the electromagnetic waves is the product of a fictitious area called the effective aperture area, AE, with the flux density of the electromagnetic waves falling perpendicular over this area. So this is what is shown here. So this S is the flux density and AE is the effective aperture area, and this is the power produced by the antenna. Okay. Aperture efficiency of an antenna. Again, there is another term related with the aperture, and many other things will come up. Okay, this is the aperture efficiency defined as we will read this one. The effective aperture area is specific for different type of antennas. For example, the effective aperture area of a dish antenna could be equal to the physical cross-sectional area of the dish if the antenna is lossless. Whereas for a dipole antenna, this area is generally more than its physical area. The effective usage of physical aperture depends on the aperture efficiency of the antenna, which is the ratio of effective aperture area AE to the physical area AE of the antenna, and is expressed below. Well, if you, as I said that the aperture area or effective aperture area, these are actually one or other way of expressing the power conversion factor. So, for example, if you take a dish antenna, in the dish antenna you will see the cross-sectional area of the dish, the pi r square. That is its aperture area. So, it will be able to collect that much amount of electromagnetic waves falling directly or perpendicular to the that area, and it will be able to convert to power. But in actual case, it doesn't happen. When you make a dish antenna, you have many other things coming in, and they eat away your power. Shadow regions are formed. Many other things come inside. It plays a role. So effectively, what happens is the power expected from a dish of say 45 meters. When you construct an antenna of that, the actual power that you get from the dish is only 40% of that. 40 to 60%, that varies actually. 0.6 is a good, yes. It varies from 40 to 60%. So, therefore, though you multiply the actual area into the input flux density, you get a number, and the actual power that you get is 40% of that. So we define the area of that antenna, the physical area, as the area of that surface, whereas the effective aperture area is 0.4 or some percentage of that one. So that is the effective aperture area, and the ratio of this that I am talking about, that 40% and 60%, that is the aperture efficiency. This one. This is what it means. The effective usage of the physical aperture depends on the aperture efficiency of the antenna, which is the ratio of effective aperture area AE to the physical area AP. So this is PE stands for the physical area and is described. This is the physical area of the dish. This is the actual area calculated from the measured from the power, and the ratio of these two is the is the aperture efficiency. Some relations with wavelength, directivity, and aperture. So the effective aperture area AE is related to the wavelength lambda and the solid beam solid angle omega m subtended by the main beam is shown as. These are simple formulas. You can just take it down. These it's better to mug it up. Sometimes these comes in very handy when you are asked something. Then suddenly you don't remember the concepts, but then you will go through your memory and you will find out these equations, and then you can answer that question. So these two formulas is good to memorize. This is very much used. D is equal to 4 pi AE by lambda square, and lambda square is equal to AE into beam solid angle omega m, where lambda is the wavelength, AE is the aperture area, D is the directivity, and okay. So this is it. So just remember these two formulas. This you will be using again and again. I'll go to the next slide. Then there is a term called effective height or effective length. This application you won't find here because this is meant for wire antennas and all, or dipole antennas for which you calculate the length. Now instead of area, there are some antennas which do not have area. For example, a dish has an area, but a dipole does not have an area, because you know what you can consider the dimension of the dipole area as it's one-dimensional. So you don't have area. But then there should be some relation to multiply it with the field and to get the output power. Now here you consider it as one dimension, so you won't have area, you will have length. And length, if you multiply it with electric field, you will get voltage. If electric field is in volts per meter, then you multiply it by length, you get a voltage. So these are generally used, that's why I said that these are generally used for wire antennas. So I'll just read it. The effective height or effective length H, this H of an antenna is similar to the effective aperture area, except that it is used for calculating the potential developed across the antenna terminals of a receiving antenna from an electromagnetic wave instead of power. The output voltage V in volts across the terminal of an antenna is the product of electric field E in volts per meter with the effective height H of the antenna in meters as explained below. So this is the output voltage of the wire antenna, this is the length of the wire antenna, and this is the electric field present in the free space. So when you put that antenna in that free space, then if you know this electric field in the free space of the electromagnetic wave at any instant of time, then you can calculate the voltage at that instant of time by just multiplying by the length of that effective height of that antenna. The above equation is useful when working with wire antennas whose physical aperture area is almost negligible. Then one more thing to remember, that in some of the antennas, though it do not have a physical aperture area, but it has an effective aperture area. For example, a dipole antenna does have an effective aperture area, otherwise it will not be able to convert it into power. So you need both dimensions. So it has an effective aperture area, but physically there is no such area because it is one dimensional. Physical dimension is only one. Don't get confused. Okay. Now there is a antenna reciprocity theorem. So this is very important. people forget about it. We ask them in their interviews and all. People are confused about this, and they are not able to answer this many of the times. Even most of the antenna things, I think people just are not able to answer. So I thought that it is better to make them up to date for this, and this should not be forgotten for any RF engineer working in a place like GMRT. They should never forget these things. So there are several versions of reciprocity theorem that is used in circuits, and in circuits there is a reciprocity theorem. I think the theorem is same, except that the theorem is based on the voltage and current relationship. Voltage at one end and current measured at the other end. That is the theorem. When you reverse the sources, voltage source, you bring the voltage source at the other end, then and you measure the current at the opposite end, you get the relation to be same. That is the principle of reciprocity. Now here, how do we do it for an antenna? So you have two antennas, antenna 1 and antenna 2, and these are facing each other so that waves can propagate from this one to this one, or waves can propagate from this one to this one. And this propagating medium is the free space. Now, you have a voltmeter at this end. You have this is the source antenna. So you have connected to a source here. This is the source here connected to this. And to measure the source voltage, you put a voltmeter here. On the other side, this is your load antenna, where you have connected a load resistance here. So whatever power it reduces will be coming here. Some portion will be captured by this and converted back to power, and then this power will be dissipated in this load. And you have a ammeter for measuring the current. So what the theorem says is that if this source impedance is same as this load impedance, then this theorem is valid. In that case, what you will see is whatever voltage you measure here and the current you measure here, you take a ratio of these two, V by I. You keep it, note it down somewhere. Then what you do is you remove this portion, connect it this side, and this portion you connect it this side, and again measure the current. So what you will see now, this side, that V by and this side I, this V divided by this I will be same as the previous one. So that is what is the reciprocity theorem. And this is same for in electrical circuits and all. It is also same. So in any point in the circuit, you feed a voltage, and in some other point in the network, you measure the current, and then you reverse it, and you get the same relationship. The relationship does not change. That is the reciprocity theorem. Now, I will read it. If an EMF is applied to the terminals of antenna 1, this EMF is applied, automatic force, and the current is measured at the terminals of antenna 2 using this ammeter. Then an equal current in both amplitude and phase will be obtained at the terminals of antenna 1 if the EMF is applied at the terminals of antenna 2. That is what it says. Only thing is that I have not mentioned about phase. Now here it says the phase also should be same. That is the phase of this current with respect to V, that is in the ratio of V by I, that one, that phase, or that means that impedance formed by V by I will be same as in opposite way. I mean, when you connect this one on this side and you measure the current on this side. So that phase relationship should also be maintained. That is what it says. The theorem is valid if the impedance of the signal generator and the load across the antenna 2 is 0. The signal, the theorem is valid if the signal generator and the load across antenna 2 is 0. This something I have to correct this one. There is just ignore this statement. Practically all signal generators have non-zero impedance. Thus, it is necessary to have identical impedances of same generator and load. Now, there are certain applications, I mean, in radio astronomy, you use the reciprocity for engineering purposes, like most common applications are the radiation pattern of an antenna is unchanged when used as a receiver or transmitter. So, reciprocity also proves that whether you use the antenna as a receiving antenna or a transmitting antenna, its properties does not change. So therefore, if you measure the receiving property of the antenna, you use the antenna as a transmitter to radiate, and you don't have to do a measurement again for the antenna when it is used as a transmitter. You can consider the receiving properties to be the same as that of the transmitting properties. So therefore, radiation patterns of radio telescope antenna feeds can be measured in the transmitting mode or in the receiving mode, whichever you want, in the anechoic chamber, and you can put it on the dish. The impedance of antenna does not change when used in the transmitting mode or in the receiving mode. The impedance of radio astronomical antenna feeds can be measured inside an anechoic chamber. It's all same actually. Here it's considered some measuring of the impedance of that using the reciprocity theorem. The main thing is that you measure it, and then when you apply it as a receiving or a transmitting thing, it doesn't change, and that way you can characterize your systems before putting it for actual use. The theorem fails, this is very important, the theorem fails when the propagation of radio waves is highly affected by the presence of Earth's magnetic field and disturbances created in the ionosphere. So they do modify the results that come. I will talk about these ionospheric disturbances and all. I think many of them who have a communication background, they may be knowing about it, but we will talk about this later. But just remember that they occur for, these things are valid only when they are in ideal conditions. Then there is another term called antenna bandwidth, which is a loose definition. There is no definition for antenna bandwidth. You can search the entire Google and or any kind of books, and you won't find this one, because the reason is defining a definition of antenna bandwidth is bogus, because you want the antenna to work within some band. Okay, so you design that one, provided your matchings and everything remains same in that one. Your VSWR remains same and all, but that doesn't happen always. So then how do you define the antenna bandwidth? Bandwidth has to be defined over for which certain properties of the antenna remains under specific values. So it is just you can define your own bandwidth, that I am defining my bandwidth by considering the VSWR to be so and so below this. So it is just a user's definition, I would say. But then for resonant antennas are antennas like dipole antennas, where ideally this should be resonant at a particular frequency, and its characteristics should peak at that resonant frequency, and it will fall on either sides of that frequency. So those kind of antennas are called resonant antennas, for which you can simply use the definition of bandwidth as using the quality factor and center frequency. So the antenna bandwidth delta F is equal to F resonant by the quality factor Q, and quality factor Q is again is another definition. You can find it out. The total energy stored by the antenna by energy dissipated or radiated per cycle. So I'll just read it. These are very loose concepts. I mean, this one is okay. This is okay, but then this is only for some antenna which has a very narrow bandwidth. And nowadays we don't require, I mean, these kind of antennas are very rarely, of course, usage is there in case of, let us say, radio and all. I mean, many places users are there, but then here in this center, we may not be seeing it. Anyway, the bandwidth of antenna is difficult to define, since the antenna properties like radiation pattern, radiation resistance, etc. changes with frequency of operation. Therefore, the bandwidth or is defined in such a way that certain properties of the antenna meet certain specifications. I think this is what I said. Generally, the bandwidth is measured categorically. So these are some types in which you can measure the bandwidth. Bandwidth over which the directivity of the antenna is higher than some acceptable value. So this is one. So your antenna may be radiating, its VSWR may be good, but your pattern changes and it goes away and it radiates in some other direction. So what is the use of that? So then you measure the bandwidth over which your directivity remains in the same direction and is higher than certain particular value. Then bandwidth over which at least a specific front to back ratio is made. This is again another way you can specify your bandwidth, that my antenna has this much front to back ratio over this band. Then bandwidth over which the VSWR of the transmission line can be maintained over any specified value. Okay. Okay, I think I have no time to derive these equations, so you can. It's not very important also for our purposes. I know everybody has done this one in their electromagnetics. I think everybody has done this one. I'll just simply recap this one. So this is a dipole antenna. You can see the current distribution. So you see the current will be maximum at the center and minimum at the two ends. Whereas if you take the voltage distribution, this will be like this. You will see that voltage will be maximum at this side and the current. Yeah, this is the current distribution. So yeah, this is the current distribution. I naught into j omega t cos theta L. Yeah, right. And the voltage will be like this. So the equation of the electric field variation across the dipole as a function of time is. This is the equation for that one, and if you see the this is the H plane and this is the E plane, and you cut the radiation pattern, and then you get the expression. You can calculate the expression for the electric field. This is what it is. Radiation resistance is given like this, which if you evaluate it, it will come to around 73.13 ohm. And then directivity, you can calculate it using this expression. That will come to around 2.15 dBi. So what is important is this figure. So for a dipole, half wave dipole, this length is lambda by 2. For a half wave dipole, you should know that the radiation resistance is this much, and its directivity is 1.64 or 2.15 dBi. This an engineer should not forget. This diagram I have already shown you in the beginning, that an apple cut into 3 pieces. Now we come to the, I think probably this is the last part of it. This is another very useful concept. For this concept we generally use for mapping the, in the imaging we use this concept for mapping the source intensity with the aperture of the antenna, physical aperture or whatever, not physical aperture, aperture found by the data with that spread over the UV plane. So for that, here our aim is to show that, or aim or whatever it is, we will show that there is a relationship between the field at the source, the electric field at the astronomical radio source, and the electric field on the aperture of the antenna. So that relation we are trying to put it out. So a simple technique would be to use the concept of angular spectrum. The electric field Ex in the aperture of an antenna. So this is the antenna and this is the aperture. It may be thought to be as composed of interference created by a continuum of plane evanescent waves propagating in various angular directions phi. So you can consider that this electric field is built up of several electromagnetic waves that are coming or going from this. Okay, so that is why it says the interference created by a continuum of plane evanescent waves, and these waves we are considering it as having plane are having plane wave fronts. So that means if these are plane wave fronts, then they have to be from very large distance. Now, if you represent a plane wave of fixed frequency nu as some function of this phi, this angle in which it is coming for one particular wave, and this is the propagating factor, that is omega t minus beta z. If you remember that, this is the directional part and this is the time part. This will give the wave to jump up and down, and this will make the wave to go. So this j omega t minus beta z, this is what e to the power. So if this term is there in any equation, you should know that this is a traveling wave. And r phi is the direction of propagation. This should be a it's a wave vector quantity, not written very clearly here. Now this should be k dot r phi. Actually, it should be. I have not written it properly. The electric field E may be represented as the sum of continuum consisting of infinite spatial frequencies. Okay, then again we come to the spatial frequencies. Last time I gave you a vague idea that you have an electromagnetic wave stretched out in space. Now, if you have the length of if you increase the frequency, more waves can be accommodated in that space. And depending on the length of the space used, the spatial frequency is inverse relation to that. So anyway, we will come to more descriptions later. For the time being, you can think about that spatial frequencies is a dimensional concept, or a physical dimension of the frequency, or of the wave, physical dimension of the wave. That way you can think about. So the electric field E may be represented as the sum of the continuum consisting of infinite spatial frequencies. That is Fourier transform of this particular this f phi is phi here. So this is equal to you can see this is some kind of Fourier transform dx by lambda. If you consider x by lambda to be tau or something, so this will be d tau. This is the infinitesimal differential element, and again e of tau or something like that. So what our aim is that if we establish the relationship only in the aperture plane of the antenna using direction cosines of the wave, what we obtain is called the angular spectrum of the antenna, as shown next. When you see the next part, then things will become more clear. See, here we are giving you a template. This is the template, and then how you relate using this template the electric field here and the far distant electric field of the source. So here is the relationship. First we consider a single dimension, one-dimensional case. This is two-dimensional, this is one-dimensional. This radiation pattern is in one dimension, one plane. This is in two dimensions. So the earlier equation you saw that P of psi is equal to something. So instead of P of psi, now it becomes P of sin psi, and sin psi is the direction cosine. And again this psi, this in the Fourier transform, that psi, earlier you had this Fourier transform equation like this. This psi, if you replace it by sine of psi, so then you can get this one. And so the electric field, and from this you can find the reverse equation. So this is the far field, and this is the aperture field, you can see. So the aperture field is related to the far field using this direction cosine sin phi. So instead of you don't have phi here, but you have a sine over this 5. So this is very important. It is very simple also, and very important to remember that you can always calculate the far field pattern at a very large distance where the waves seem to be plane waves. In 2 dimension, you just convert this into a 2-dimensional Fourier transform. So here you will have two angles. Here we have one angle phi. Here we have delta and gamma. So P of sine delta and gamma is equal to double integral of this x and y. X is this, you can call it as UV, UVW, that is similar to that, and e to the power this. And this is the Fourier transform equation. And this is the reverse Fourier transform equation. So these equations will come again and again. What I mean to say is the aperture field is related with the distant field of the source, where the waves becomes parallel, that much distance away, or like astronomical sources. We assume that when they come near the Earth's surface, they become plane waves. And so if the plane waves come from a very distant source, then you can relate the electric field distribution of that source with the electric field distribution of the aperture of your antenna, using a Fourier transform of function of direction cosines. So in the diagram which I shown earlier in previous lectures, that you have UVW in this one and LMN in the other. So L and M are the direction cosines. So direction cosines, here it is this sine of delta, sine of delta, sine of gamma. These are direction cosines for this. I will give you the slides, so you don't have to take it down if you don't want. I will go to the next one. So this is just a few words about polarization. I will take a separate chapter on this one. I have a separate chapter. Many things I will be talking there. So I will just read it, this one. I am not going to much explanation of this. The antenna is usually polarized. The electric and magnetic fields lie perpendicular to each other and to the direction of propagation. As the wave progresses, it travels through space. The electric field and the magnetic field may continue to lie in the same plane or change its orientation with each wavelength traveled. For the former case, the wave is said to be linearly polarized, while in the later case, the wave could be circularly or elliptically polarized, depending on whether the amplitude of the electric field remains fixed or change with angle respectively. The circular or elliptical polarization can again be classified as left circular elliptical or right circular elliptical, depending on the directions in which the plane of polarization rotates. The dipole type antennas are linearly polarized, whereas helical antennas are circularly polarized. So these are some two type of antennas which can generate two type of polarizations: right circular, left circular, elliptical. All those things we have already talked about it in the beginning class. But then I will take a separate class for this. Maybe in the next lecture. I don't know when it will be, because Friday is a holiday, and I will not take it on Friday. And okay, I will discuss it after the class. Okay, here we come to some properties of astronomical sources. These are also very self-explanatory. I need not explain, I will just read it. Astronomical radio sources have the possibility of all type of polarizations. This can be linear, elliptical, circular, random, or combination of random polarization with remaining types. This is the general type of which is they are actually mostly random and maybe little bit of other. That is the astronomical sources characteristics of polarization. A complete information of the astronomical source can be obtained by using two linearly polarized antennas. You can get the information of polarization if you have two antennas, orthogonal antennas, Orthogonal in the sense means if their plane of polarization at any instant of time should be orthogonal to each other, should be 90 degrees. Then only they will be able to do. For example, you take two dipoles, and then if you place perpendicular to each other, and again the plane of this antenna should be perpendicular to the plane of propagating waves. So you will be able to receive all the information of polarization, provided you have these two orthogonal. Yes. So two linearly polarized antennas with their planes of polarization perpendicular to each other, that's what it means, or two circularly polarized antennas having opposite polarizations, left and right circular. In this case, you have to keep the two antennas having two different type of polarizations. One should be left circular, one should be right circular. And in other words, the signal that is coming, you have to break it into two components, which you can again join them and to form the original signal. If the single polarized antenna is used for receiving from an unpolarized source, only half of the flux density is received. An unpolarized source is like incoherent noise source of equal strength connected to linearly polarized antennas positioned perpendicular to one another. You can try this one. Two circularly polarized antennas, one left and one right circular, may also be used instead. I think you had it what you wanted. And these are some assignment problems. If you want to, you can discuss if you want, but I'll just give you hints for this. This is the explain the mechanism for radio and reception using an antenna. This you will find in this video in the first portion, if anybody has missed that one. And explain the concept of isotropic antenna. This we have learned this one. Explain the diagram of explain with a diagram reactive field region, radiative. This is the three regions which we described. Difference between what is the difference between Fresnel zone and Fraunhofer zone. So these are identified by the formulas that are used, and also I said about the 1 by R, 1 by R square, 1 by R cube. So these actually differentiates. What is meant by radiation pattern of an antenna? You know that. Explain the various lobes of an antenna using a diagram. That is a lobe diagram, where at the side lobes, back lobes, and other things that you need to explain. Using a diagram, explain the concepts of half power beamwidth. These are the descriptions, definitions. Using those definitions, you have to do this one. Then front to back ratio, you know that. A normalized radiation pattern of an antenna, that PN. PN is the normalized radiation pattern. The radiation pattern divided by its maximum value. That is the normalized radiation pattern. What is the directivity of an isotropic antenna? You know that what is directivity. So hint is given here. Antenna has a directivity of so and so. Calculate the effective aperture area. So I have given you all the hints. The hints are given here. Just try this one. These equations. I think you can do this one. The physical cross-section area of a paraboloid dish antenna is so and so. If it has an effective aperture area of 60 meters, calculate the aperture efficiency. These things. For you, you are nodding your head. I know you know that. Other people should do that. You did not solve this because you know these things. I know. So it's okay. For you, it is okay, but for other people. Then radiation resistance of an antenna is 73 ohms, and dissipative resistance. This is the loss resistance I am talking about. Dissipative resistance is the loss resistance. What is the antenna efficiency? This can be calculated. Using the same antenna efficiency, calculate the gain of antenna if directivity is. All these things I think I have given in this. Let us see. The flux density falling into an antenna having an effective aperture area of so and so is this much. Assume the antenna to be 100% efficient. Calculate the power delivery. Simple equations. If you don't, you can ask your colleagues, or if you are not able to do it, you come to me, I will solve it. I think these are simple. Many of you can ask him. Gaurav, you can ask Gaurav also. So he will be able to solve many of these. Here, electric field of an electromagnetic wave falling on an antenna of effective length 1 meter and okay. This is, let me see. This is the antenna reciprocity theorem. Describe half-wave dipole, directivity of an antenna. All these things you can do it linearly. Explain the concept of angular spectrum. This may be slightly difficult because I know that people have not understood this one. But I have not given much importance to this one in explaining this angular spectrum. The best way is that see, we are concerned about this application, so I have given you in the simplest form. But if you really want to understand, you need to see the you need to see in the Google that what is the meaning of this angular spectrum. This you have to work it out. What I have given here, I think it is not sufficient. The formulas are sufficient for usage. I have given you how the near and far fields are related, but angular spectrum I have not described it very clearly. Then what is meant by polarization of an antenna? That is and here we come to the end of this lecture. I will stop here. Okay.